Hi, this is Dr. Bricker here with Homework 3 hints. Homework 3 is actually due on Monday at 4:59 p.m. right before the test. So this material from Chapter 3 is fair game for the test. Okay, great. So first problem, 3.01, is all about breaking forces into components. So review the Chapter 3 notes if you're a little need a little refresher on a little trigonometry, sines and cosines, things like that. 3.07 takes it to the next level, really. It's the problem with a knot, and there are three forces acting on the knot. If you take a look at Figure 2, you'll see a little bit better of a picture, something that looks like this. So we have T2 this direction. At 53 degrees, you might have slightly different numbers. T3 is to the left. T1 is down. Okay? And in the problem, we're given that T1 is 300 newtons, and the knot's not going anywhere, so all of the forces are balanced. So if there's 300 newtons down here, the y component of T2 has to also be 300 newtons for the forces to be balanced. So I put this on the picture here. T2 and the y is 300. So if you know the angle, you know T2 and the y, you could use some trigonometry to figure out T2 then. So from the picture, we see that the sine of 53 degrees is the opposite side, which is 300 newtons, divided by the hypotenuse, which is T2. A little more algebra. T2 turns out to be 300 newtons divided by the sine of 53, doing some algebra on this expression, or 376 newtons. Horizontal forces are also balanced. So T2 in the x here has to be equal to T3 here. And I wrote that here. So the cosine of 53 is the adjacent side, T2 in the x, divided by the hypotenuse. Now we actually know what T2 is, so we can solve for T2 in the x. So T2 in the x is T2 cosine of 53. And again, T2 in the x is equal to T3. Kind of a neat problem. So number 20, I go over in Chapter 3 notes. It's the accelerometer, and this allows you to figure out the acceleration. So take a look back at the notes to figure out what the acceleration of this, I think it's a washer in the problem. One little tricky thing, not really tricky, just a detail. The washer is 10 grams, so you've got to change that into kilograms. So divide 10 by 1,000 to get it into kilograms. Okay, and then number 22, I think it's a skier on an incline. There's no friction. This is also in the notes for Chapter 3. But as a reminder, here's an incline here, angle theta. With these incline problems, we know that the motion is along the incline, so it simplifies these sort of problems to think of this as being the x direction and this as being the y direction. So here's the free body diagram. Normal force perpendicular to the incline. mg is straight down. And in the notes and in the chapter, you see that this side here, pointing down the incline, whoops, I got it backwards actually. This is mg sine theta. And perpendicular to the incline is mg cosine theta. So we want to figure out the acceleration down the incline. We could use Newton's second law. Net force is ma, and I put a little x there just to emphasize the fact that it's down the incline. And then when you look at the free body diagram, the only force down the incline is mg sine theta. So I have this here, and you can solve for the acceleration then. In the y direction, the normal force is equal to mg cosine theta. The skier's not going off the incline or through the incline, so those have to be balanced. So you can get the normal force that way. Part C and D, they actually give you this displacement down the incline, so you can use kinematics equations to figure out the quantities in that part. Okay, number 27, we're dealing with a couple of wagons connected by a rope, a horizontal rope, T2, being pulled by another rope, T1, at some angle. In my question, the mass of the wagons are each 30. theta is 37. You might have slightly different numbers. And the acceleration is 2 meters per second squared. And we're asked to find T1 and T2. I find the easiest way to get T1 is actually to look at the wagons as a system, as both wagons. My picture's not that great. This is supposed to be up. This is supposed to be straight down. But we have T1 this way. Again, this is both wagons at the same time. T2 is an internal force in that case. And then we have the weight down, so 2m times g, because remember there's both wagons. We've got T1 here, so there's a T1 in the x direction. There's also a T1 in the y direction. I don't think that'll really help us solve the problem, but just to be complete. And then we can use Newton's second law. The net force is ma. In this case, it's two wagons, so 2ma. And I'm looking in the horizontal direction. The only force we have there is T1 in the x. So T1 in the x, which is T1 cosine theta, when you look at this picture. Cosine of theta adjacent over hypotenuse. And then you can solve for T1, which I've done here. The next part of the question is to figure out T2. So now I'm just looking at the forces on the first wagon. So again, we've got T1 at some angle given in the problem, normal force, mg, just a single m because I'm only looking at the first wagon, and then a T2 back the other way. So the net force is ma, and we've got a T1x to the right, a T2 back to the left, a little bit of algebra to come up with T2. So T2 is T1 in the x, which you know from the first part. You can solve for it anyway. T1 cosine theta minus ma. You could have done a free body diagram of the second wagon. That might actually be a little bit easier. T2, here's the normal force, here's mg. This is of the second wagon. And then you'd have the net force is ma, and the only horizontal force is T2. So T2 is ma. Actually, that's a lot easier. Okay, but either way, it should come out. Either way will give you the correct T2. It's a way to check yourself, actually. Okay, moving on. Number 25. It's a person in a car. There's a force downward here at an angle of 37 degrees. We're given that the acceleration in the x is 350 meters per second squared. And we want to figure out f sub x. So this one's not too bad, actually. ma, net force is ma. You have to supply the right-hand side over here, just like always. And the only force, horizontally speaking, is f sub x. So you can get f sub x there. And then a little trigonometry, cosine theta, f sub x over f, and solve for f that way. Okay. In number 38, we're really asked to figure out what's the maximum amount of static friction you have to overcome to get this object moving. So the coefficient of static friction is given, 0.5 in my case. Mass is given. You might have a slightly different number again. So the maximum static friction is when it's equal to the normal times mu sub s. And the normal in this case is mg. So maximum static friction would be this amount. So you have to put a force in slightly greater than that to get this thing moving. Okay, so number 43, in some sense, is maybe the hardest one on the whole homework, in my opinion. So we have an object. We're moving it with a force that is downward. So when you move a box or whatever it is, by pushing downward, you actually increase the frictional force. The reason is, if you have a force at this angle, it's got a y component here, so you actually increase the normal force over, it's greater than mg. In this case, normal force is up, mg and f sub y are both down, so you've increased the normal force and you've increased friction. In this problem, another key part is moving at a constant velocity. That means the horizontal forces are equal to each other. So as I have here, kinetic friction back to the left is equal to f sub x to the right. They're equal to each other because the velocity is constant. Okay, good. And the task is to figure out what this force is. Okay, good. So It's moving, but it's not accelerating, so horizontal forces are balanced. So kinetic friction is equal to F sub x. Here's a definition of kinetic friction, normal times mu sub k, and that's equal to F sub x, which in this case will be F cosine theta. As I said, the normal force is greater than just mg. It's equal to mg plus F sub x. So I'm trying to figure out F here. I have to put in the normal force to do that. Normal is mg plus F sub x. So mg F sine theta. So I can put this whole thing in for the normal force then. Remember, I'm trying to figure out F. I can't do it yet because I don't know n. My next step is, oh, maybe I can write n in a different way, and that's what I'm doing here. So then I can put this in for n. So mg plus F sine theta is n, and then times mu sub k is F cosine theta. So as you notice, the only thing that you don't know in this expression is F. A few steps of algebra to recover F. So you've got to get F on one side of the equation by itself. Everything else will be on the right-hand side. Just be careful with the algebra, and you should be able to get F that way. Once you have F, everything else falls into line. For example, another part is figure out the normal force. Well, the normal force here is equal to mg plus F sine theta. So when you have F, you can get the normal force. Another part is to get kinetic friction. From here we know kinetic friction is F sub x, so you can get it that way. Again, this is a little time consuming, this problem, but hopefully once you get F, everything will fall into place. Okay, number 46 is a car stopping. We're given the mass. You might have a different mass again. Initial velocity and mu sub k. Here's the free body diagram. Kinetic friction back to the left, normal, and mg. Back to Newton's second law again. Net force is ma. Look at the picture. What is the net force, horizontally speaking? And it's kinetic friction here. Here's the definition of kinetic friction. Normal times mu sub k. Back to the regular normal is equal to mg part, and you can solve for the acceleration. And then use kinematics to figure out how far the car actually travels. Okay. Lots of hard work on this homework assignment. 57, there's no numbers to punch in. It's just looking at free body diagrams. So it's a bowling ball rolling on a table, then it leaves the table, and it's just under the influence of gravity. So while it's on the table, we have a normal force up, mg down. That's while it's on the table. Once it leaves the table, it's just the weight. I think they call it force of Earth on object, or something like that on the actual homework. So the first part, free body diagram while it's on the table, that's what we have. It's already moving along. We're assuming there's no friction, normal, mg. Once it leaves the table, the whole time, this is the free body diagram. It's just gravity. Okay, baseball season for number 60. It's a ball that leaves a bat. It's flying out towards center field. We want to know something about the forces acting on it. So we've got mg down the whole time. And in this one, they want us to consider air resistance. So I just call it a drag force. So it's opposite the direction of motion and outward from center field. Okay, that'll make more sense when you see it on the Mastering Physics homework. Okay, here's a projectile motion problem. It's a tennis ball being served from a height of 2.4 meters at a speed of 22.3. You might have different numbers. The key thing is this speed is horizontal. So the initial velocity in the y direction is 0. That simplifies things a lot. In my problem, I'm 11.9 meters from the net, and the net is 0.91 meters high. So the first part is, will it clear the net, and when it's over the net, where is it located? What's the coordinate? Okay, so with projectile motion, you have to think of the x and y direction separately. The thing that ties both of these together, though, is the time. So what we can do is figure out how long it takes to move over 11.9 meters in the x direction. Once we know how long it takes to move over 11.9 meters, we can see how far it's fallen in the y direction in that same amount of time. Okay, so x direction, velocity in the x, delta x over t. Figure out how long it will take to go over, using x information, and then figure out where it's located in the y direction. We've got all the kinematics equations to work with. I think this one will actually be useful here. Delta y, initial velocity times time, which the initial velocity is 0, so plus 1/2 at squared. And this t we just found from the first part. So you can figure out how far it's dropped in the y direction to figure out if it's gone over the net or not. Okay, so start with the x direction to get the time, figure out the y displacement using that time. Part C and D, we want to know if it lands in the service court. So this is the whole court here, whole side, here's the net. We want to know if it lands here, somewhere in the 6.4 meters. So what we can do is figure out how long it will take to drop 2.4 meters. Right, in the y direction, that's going to be the displacement. So for delta y is minus 2.4, what is the time? So the time to drop this distance, use that time to figure out how far over we go in the x direction. Okay, and you can then see, if it's greater than this combined distance, it does not land there. If it's less, it does land. This is number 64 is rivaling the other problem for the most difficult one on this set, I would say. Finally, we have Robin Hood shooting an arrow. So if you aim directly at the target, you're never going to hit the target. You have to actually aim somewhat above the target. So if you're playing darts or something like that and you aim right at the bullseye, you're never going to get the bullseye if you try to throw it horizontally. As soon as it leaves your hand, it's under the influence of gravity and it sinks down a little. So you actually have to aim over it, and if you play darts, eventually your mind and your hand are in unison, and you don't even think about it, but you're really aiming above it, and it's coming back down. So in this problem, it's thrown horizontally again, so the initial velocity in the y is 0. We can figure out how long it takes the dart to move over 40 meters, and then use that time to figure out how far it changes in the y direction. So use the x information to figure out how long it takes to get to the target, this 40 meters. That's what I've done here. And then using that time, we can figure out how far it sinks down in the y direction. Again, acceleration in the y, negative 9.8 meters per second squared. So then you can get delta y this way. This number actually comes out negative, but the Mastering Physics just wants the distance that it falls, so you don't have to enter the negative amount. Okay, lots of work ahead. 13 questions on this homework assignment. Some are more difficult than others. We have several days to get it done, and I'll be in contact with you.